In this video, we are going to do some exercises on functions and countability and uncountability of sets. For our first problem, suppose that we have a relation R from N to Q defined by A is related to B if 3A plus 5B is equal to 1. Let us determine if it is a function. So first, let us write the definition of a function. Our R here, so supposedly it's from N to Q. So the definition says that if we get an arbitrary element in the domain, then there must exist a unique element in the codomain such that AB is in R. Since we have here for all A in N, we start our proof with, if ever this is a function, with getting an arbitrary element in N. So this one has two parts for the existence part. So we have to find our B. There exists a B in Q such that AB is in R. However, if we solve for B here, what do we get? Our B here is equal to 1 minus 3A over 5. So we just say, take B to be equal to 1 minus 3A over 5, and then we will show that this B here satisfies this, that AB is an element of R. So we just say, note that 3A plus 5 times, oops, this one should be all over 5. 5 times 1 minus 3A over 5 is equal to 1. So thus, our AB is an element of R because it satisfies the required equation. So that is the existence part. Next, we have our uniqueness part. For our uniqueness part, notice that I have already my A here. For the uniqueness part, suppose that there are two B's which satisfy this. By the way, I didn't mention earlier, take note that this B here is really an element, so that is very important. That is an element of the set of rationals because A is a natural number. So that's very important. You have to really show that your choice of B should be in the desired set. So for the uniqueness, so suppose B1 and B2 are two rational numbers such that AB1 is in R and AB2 is in R. But this would mean that by definition, 3A plus 5B1 is equal to 1. And this one is also equal to 3A plus 5B2. From this equation, we can now get that B1 is equal to B2. So therefore, our B is unique. So therefore, R is a function. Next, we have another relation here from A to B. Our A and B are just finite sets. We have A is related to B by the relation F if 5 divides AB plus 1. Is F a function? So since our domain here just consists of 3 elements, all we have to do is to get the corresponding images. So for A equals 2, let us find the corresponding B. So what will be our B? We want 5 to divide 2B plus 1. And what will be the only possible b here? If b is equal to 1, we have 3, so 5 does not divide 3. If it's 3, 7. 5 does not divide 7. And then if it's 4, this would be 9. If it's 7, 7 times 2, 14, plus 1, 15. So therefore, 7 is a good choice for B. What about 9? 9 times 2, 18, plus 1 is 19. So therefore, we have only one B, and that B is equal to 7. What about if A is equal to 4? What will be our B? We want 5 to divide 4B plus 1. So what will it be? If it's 1, we have 4 plus 1. So that's B equals 1. Correct? Is that the only choice for B? We have to make sure that that is the only choice for B. If B is equal to 3, we have 12 plus 1, 13. No, 5 does not divide that. If it's 4, 16 plus 1, 17. If it's 7, 28 plus 1 is 21, 29. And then if B is 9, this would be 9 times 4, 36 plus 1, 37. So, okay, we're good. B is equal to 1. Lastly, let's check for A equals 6. So, we want 5 to divide 6B plus 1. If B is equal to 1, so this is 7. If this is 3, 18 plus 1 is 19. If this is 4, 24 plus 1 is 25. So B is equal to 4. Let's try the other B's. If it's 7, 7 times 6 is 42, plus 1 is 43. So no. If it's 9, 9 times 6 is 54, plus 1, that is 55. So therefore, B can also be equal to 9 here. So this means that there are two values of B for A equals 6. So let me just write it. 6, 4, and 6, 9 are elements of F. And therefore, this is not a function. Next, let us prove that the function from Z4 to Z4 defined by this is a well-defined bijective function. So it already says here that this is a function. We just have to show that it is well-defined and it is bijective. That is, it is both injective and surjective. So first, let me start in showing that it is well-defined. So let us recall when we say that a function is well-defined, it means that if we have the same pre-image, then we have the same image. So mathematically speaking, in terms of our function f here, this would translate to be, so if we have f of, let's say, A, same pre-image, so meaning to say we should start with if A is equal to B, then they should have the same image. F of A should be equal to F of B. And then for our quantifier, so for all A and B in Z4. Okay, this is what we want to show. All right then. So we start with let A and B be elements of Z4 because that takes care of that. And then suppose that A is equal to B. We want to show that their images are the same. So we will now compute our f of A and f of B. But from the definition, f of A is 3A plus 1. So we want to show that 3A plus 1 is equal to 3B plus 1. That is the image. This is the image of A under F. This is the image of B under F. How do we show that two equivalence classes are equal? In showing that two equivalence classes are equal, we just have to show that the representatives are equivalent. So to show that 3A plus 1 equivalence class is the same as 3B plus 1, we will show that 3A plus 1 is congruent to 3B plus 1 modulo 4. The representatives are equivalent under the equivalence relation. Okay, so remember, this is not part of the proof. I just want to show you what we need to do. So we have here, so let's go back to where we stopped. We just have that the equivalence class of A is the same as the equivalence class of B. So that means, so we have, hence, A is congruent to B mod 4. But from our properties of modulo n, we can multiply both sides by 3, and we can also add. The addition property also holds. And therefore, 3A plus 1 is equal to 3B plus 1. And this is now your f of A, and this is your f of B. So therefore, f is well defined. Now, to show that it is bijective, again, since our Z4 just contains 5 elements, I will just try to get the images of all the elements of Z4. So our f of 0 is equal to 1. Our f of 1 is equal to 3 times 1 plus 1. So that's 4, which is equal to 0. F of 2 is equal to 2 times 3, 6 plus 1, modulo 7 is 3, and f of 3 is, remember, we are taking it to 3A plus 1. This is our f of A. So 3 times 3, 9 plus 1, 10, modulo 4 is 2. Now, therefore, by looking at this one, we can now say that f is injective, correct? And moreover, f is surjective because these are also all the elements of Z4 already. So just for you to imagine what's going on. So it's like this. We have 0, 1, 2, 3. 0 goes to 1, 1 goes to 0, 2 goes to 3, and 3 goes to 2. And these are actually your equivalence classes. Suppose that we have A is the set of even integers and B is the set of odd integers. And then we have this function defined by, so this is from A cross B, so Cartesian product. So this is an ordered pair. It goes to B cross A. So notice here that what does it do? It takes AB to the sum. We get the sum of this, and then we copy the first element here. Similarly, with G, we get the sum, and then we copy the first element. So you might be thinking, isn't it true that F and G are the same? Because that is basically what it's doing. It's getting the sum and then copying the first element as your second element in your ordered pair. However, they are not the same because they have different domain and codomain. Okay? So let's look at A. This is just direct computation. G circle F of 1811. So this is G of F of 1811. So we get the sum of 18 plus 11. So that's 29. And then copy the first element. So that is your F of 1811. And then for G of 2918, we get the sum of 29 and 18, which is 47. And then we copy the first element, which is 29. Let's look at letter B. Determine whether the function is 1 to 1. So to show that a function is 1 to 1, in layman's term, it just means that if we have the same image, then we have same pre-image. So we have, if G circle F of, what do we put here? The input is coming from A cross B. So I'll write here A1, B1 is equal to G circle F of A2, B2. Then we should have that A1, B1 is the same as A2, B2. What will be our quantifier here? So this is for all A1, B1, A2, B2 element of your domain. Okay? So let us start. So let A1, B1 and A2, B2 be arbitrary elements of A cross B, and then suppose G circle F of A1, B1 is the same as G circle F of A2, B2. We want to show that A1, B1 is equal to A2, B2. Let me just write it here. When it's in purple, that means it's not part of the proof. I just want you to see where you are going. Okay, so let us now compute G circle F of A1, B1. So that's G of F of A1, B1 is add the A1 and B1 and then copy the first element. So that's A1 plus B1, copy A1. So similarly, F of A2, B2, the sum of A2 and B2, and then copy the first element in the ordered pair. Similarly for G, we add the two elements in the ordered pair. So that's 2A1 plus B1, and then copy the first element, A1 plus B1. On the right hand side, we have the sum is 2A2 plus B2 and then A2 plus B2. So we are saying that these two are equal. So therefore, by definition of equal ordered pairs, that means that they must be equal component-wise. So thus, 2A1 plus B1 is equal to 2A2 plus B2 and A1 plus B1 is equal to A2 plus B2. Now, note that if we subtract it, what do we get? We get that A1 is equal to A2. And so, again, when we substitute it here, we also get that B1 is also equal to B2. So, therefore, A1 B1 is equal to A2 B2. So, thus, our G circle F is injective. Next, let's prove that it is surjective. What is the meaning of that? It means that if we get an arbitrary element of the codomain, so an element of the codomain is an ordered pair, right? So it's of the form B1, B2, then we should be able to find an element in the domain. So there should exist an AB in A cross B such that the image of AB under the function G circle F is the same as B1, B2. Again, in layman's term, this is saying that if we get an arbitrary element in the codomain, it will always have a corresponding pre-image. So what do we want to do here? We want to find AB. Now, note that AB is in terms of B1 and B2 because look at the statement here. We have for all B1 and B2, and this AB here depends on the choice of B1 and B2. Alright, so how do we start our proof? So this purple part is not included in the proof. This is just our guide. So we start with let B1, B2 be an element of B cross B. Now, what we want to do is to find A and B. Alright, so again, I will make this purple because we have to first find our A and B. So this is just scratch. So how do we go about it? Let's look at this one. What is G circle F of AB? From our previous computations, whenever we have, look at this one, what is the image of G circle F? What is the image of an ordered pair under G circle F? What does it do? What it does is that we have 2 times the first element plus the second element, and then the other pair in your ordered pair will just be the sum of this. So therefore, our G circle F of AB, which is supposed to be B1, B2, this is 2A plus B and then A plus B. Alright, and this one should be B1, B2. So therefore, component-wise, they should be equal. Then here, A plus B is B2. We are now solving for A and B. When we subtract the two equations, we get A is equal to B1 minus B2. And therefore, our B is equal to B2 minus A. That is from this one. And therefore, that's B2 minus A. So that's minus B1 plus B2. So this is 2B2 minus B1. So therefore, what will be our AB? Our AB is now this one, B1, B2, and then 2B2 minus B1. So since this is already a lot of scratch, I will just restart our proof here. So again, let me start with let B1, B2, B, elements of B cross B. I will just now say take AB, or actually I can refrain from doing that. I will just say that. So note that G circle F of, what is our A again? B1 minus B2. And then my B is 2B2 minus B1. 2B2 minus B1. I will show that it will be equal to B1, B2. So, the image of an ordered pair under G circle F is equal to what? It's equal to, I already forgot. So, from here, it's equal to the first element is twice the first element plus B1 and then the sum. I should just write it here. So as a guide, so if I have G circle F of star heart, it's equal to 2 star plus heart and then star plus heart. Okay? So this is equal to 2 times B1 minus B2 plus our heart is 2B2 minus B1, and then the second element in the ordered pair is just the sum of these two. So that's B1 minus B2 plus 2B2 minus B1. And this is 2B1 minus B1, so that's just B1. And then we have negative 2B2 plus 2B2, so that gets cancelled out. So that's just B1. And then here I have B1 minus B1, that's 0. 2B2 minus B2 is B2. We have to show that this one belongs in A cross B. That's important. Note that B1 minus B2, is it odd or even? Remember, B is the set of odd numbers. So if we have odd minus odd, this is even, right? This is an element of A since B1 and B2 are odd. Moreover, what about 2B2 minus B1? B2 is odd times 2, so this is even. Even minus an odd number is an odd number. So therefore, this is an element of B. And so, hence, B1, this B1 minus B2, 2B2 minus B1 is an element of A cross B. So what have we shown here? We were able to find an element of A cross B, which is the pre-image of an arbitrary element in B cross B. And now we can really conclude that F is surjective or onto. For our next example, let us show that the sets A and B have the same cardinality by finding a bijection between them. We know that Z plus is just the set of natural numbers, right? So what we can do is, in order to find that bijection, we must make the one-to-one correspondence, right? So in order to do that, N or Z plus is countable, meaning to say we can write everything without missing something, okay, and then without skipping something and without repeating, okay. So how do we list the elements of this set? So what we can do is, so this is the set 1, 2, and then Z plus is 1, 2, 3, 4, and so on. How do we list all the elements? So first, what we can do is I will write the disordered pair 1 1 2 1, right? And then 1 2 2 2. Okay? So before I proceed to the next, I just get this one, right? 1 3 2 3 and then 1 4 2 4. I am not missing anything in the set. So first we have 1 1 and then 2 1. Next, this is 2. This is for 3 and then this is for 4. Then 1 2 1 2 1 2. Okay, and this one will continue. So since this is the way we list down the elements, this will be your correspondence also with the set of natural numbers. So this is B for 1, this is for 2, 3, 4, and so on. Now, from here, let us try to make a generalization. Now, if we look at this one, the even. Okay, so what can you observe there? Look at this. 2 can be obtained from here. That is simply 1 times 2. 4 is 2 times 2. So it depends on the second coordinate. 6 is 3 times 2 and 8 is 4 times 2. And the corresponding first coordinate is always equal to 2. Correct? So we have, so we define, this will just be our scratch, our f from 1 to cross z plus 2 z plus. So what is that? If we have f of 1, the first coordinates are 2. 2m is equal to 2m, right? From here. Okay? Next, what can we say about the ordered pairs whose first coordinate is always equal to 1? So note that this is 2 times 1, but this is just minus 1 of that. For example, 3 is just 2 times 2 minus 1. Correct? This is 2 times 3. This is 2 times 3 minus 1. So therefore, we have f of 1m. This is equal to 2m minus 1. So let me just write it formally. So define f as follows. For any m in z plus, f of 1m is equal to 2m minus 1 and f of 2m is equal to 2m. Now, I will leave it up to you as an exercise. You can continue this to show that f is bijective. And therefore, after doing that, you can now see that A and B have the same cardinality. For our next example, we want to prove that these two sets are equal. Since we are showing that two sets are equal, we have to show the subset relationship. So first, again, I will no longer write down this premise. I will just proceed with this one already. So for that part, we have, suppose we will get an arbitrary element here. This is the inverse image, right? Where does the inverse image lie? In the domain or in the codomain? Recall that the inverse image always occurs in the domain, right? So suppose I'll just call it A. A is an element of F inverse U minus F inverse V. We want to show that A is an element of F inverse U minus V. Okay, so before we go there, what is the meaning of this before we proceed with our proof? A element of F inverse U minus V is just the same as saying that F of A is an element of U minus V. So therefore, we just have to show that F of A is an element of U and F of A is not in V. So that is what we want to do. Okay, so let us proceed with our proof. Suppose A is an element of inverse image of U minus the inverse image of V. So thus, A is an element of F inverse U and A is not an element of the inverse image of V, which means that F of A is in U and F of A is not in V. And that is exactly this one. So therefore, you can now go up there. So hence, F of A is an element of U minus V. So this means A is an element of the inverse image of U minus V. The other part is left as an exercise, but it's very similar to this one. Next, let us prove the following. First, the set of rationals intersection with 1, 2, the open interval 1, 2 is countable. Why is this one countable? So since this is the intersection, so we have Q intersection 1, 2 is a subset of Q, which is known to be countable, right? So, and Q is countable, then Q intersection 1, 2 is also countable. And why is that true? Any subset of a countable set is countable. Next, what about this one? The union of these sets is countable. So for this part, look at the components. Just like in part 1, each of this is countable, right? And then we have a finite union of countable sets. So from our previous results, a finite union of countable sets is countable. So you can just say that. Note that Q intersection n plus 1 is countable. Actually, that is true for any natural number n, since it is a subset of Q, which is countable. Since a finite union of countable sets is countable, then the union of Q with the open interval n plus 1 and from 1 to 20 is also countable. For our next problem, we want to show that the Cartesian product of the singleton 0 cross R is equivalent to R, and we will be using part 1 to show that the Cartesian product of the set 0, 1 and R is uncountable. Let us start with 1. So to show that these two sets are equivalent, all we have to do is to give a bijection from this set to R. And what would be the most natural function to define here? So what will be the one-to-one correspondence between this set and this set? So recall that the elements here are given by ordered pairs wherein the first element is just 0 and this is a real number. So we will relate it with what element of the set of real numbers. So we define the image of this to be equal to R, correct? And exercise. It should be easy for you to show that F is bijective. Next, to show that 0, 1 cross R is uncountable, how will we make use of the fact that we already know that this set is equivalent to R? What can you say about the set 0 cross R? Take note that this is a subset of this Cartesian product, right? However, by 1, this set here is equivalent to R, which makes this uncountable. So what do we have here? We have a set which contains an uncountable set. So therefore, this set is uncountable. Okay? So let me just write that in paragraph form. So since this is a subset of 0, 1 cross R and 0 cross R is equivalent to R, we have 0 cross R is uncountable. Recall that a set which contains an uncountable set is uncountable. So therefore, 0, 1 cross R is uncountable. Next, this example here, this last example, establishes the fact that any open interval is just equivalent to the open interval 0, 1. In our previous discussions, we have already shown that any closed interval is equivalent to the closed interval 0, 1, and the closed interval 0, 1 is equivalent to the open interval 0, 1. So what we are trying to show here is that any closed interval will also now be equivalent to its corresponding open interval. Okay? So, notice here that I have already defined the function here. What do we have here? This is a function from the open interval AB to 0, 1. We defined it as follows. And then, we want to show that this is injective. Again, that is just, that will just be left an exercise. And this one is also left as an exercise. But I think what I need to show here, what I want to do here is to really show that this function has codomain 0, 1. So let x be an element of AB. So that means x is between A and B. We want to show that its image, f of x, lies in 0, 1. What is its image? X minus A over B minus A. By the way, this one should be A is less than B. Now, if we have, so from here, x minus A is between B minus A and 0, right? We subtract A from both sides. And since B minus A is positive, the inequality will not change if we divide everything by B minus A. So we have x minus A over B minus A is between 0 to 1. So therefore, our f of x really lies in the interval 0, 1. And for number 2 also, I want to show, we really have to show first that if we get an element of 0, 1, then its image belongs in the open interval A, B. So we get an arbitrary x element of 0, 1, and we will show that its corresponding image, which is x times B minus A plus A, lies in A minus B. So we have x is between 0, 1, and therefore if I multiply both sides by B minus A, the inequality sign will not change since B minus A is positive. And then if I add A, both sides, so this will be B and this one will be A, and this is precisely your g of x. So we have g of x is really an element of the open interval AB. Now notice that this g of x here is actually the inverse of f. Since the function f here is injective, this means that the cardinality of the open interval AB is less than or equal to the cardinality of 0, 1. And similarly, part 2 tells us that 0, 1, the cardinality of this set, is less than or equal to the cardinality of AB. And this is now your Schroeder-Bernstein theorem. We have this set, the cardinality is less than or equal to 0, 1, but the cardinality of 0, 1 is less than or equal to the cardinality of AB. And therefore, so by 1 and 2, we have that 0, 1, its cardinality is the same as the cardinality of AB. So let me just write that formally, 3. So by parts 1 and 2,